the 2016 scholarship exam. Question 4. We've got nuclear physics. We have radium nucleus, initially at rest, undergoes an alpha decay according to the following alpha decay equation. So you've got radium, I should say, decaying into, pretty sure that's radon, plus an alpha particle or helium. Show that the energy liberated is 4.88 mega electron volts. So in other words, what's that, radium minus the sum of the, so this is the, what is this? These are the products. That is, I forget the name of that, I'll figure it soon. So minus Rn plus He is going to be equal to the energy liberated. So I'm going to use a delta symbol just so we don't get confused with electric fields. And that is equal to, I'm going to write this out, 22. So I'm just going to use these numbers up here. I'm going to use the AMUs first, and then I'll times by 1.66 times 10 to the negative 27. These are atomic mass units. Right, so we're going to go 22, so we have the radon, which is, radium I should say, 226.02541, I don't need the other zero though, minus, I'll check some brackets, 22.01758 plus 4.002603, and that is equal to, I've already done this on my calculator, 5.229. When you do this, you've got to be very careful typing in all the numbers. 10 to the negative 3, that's just units, not mu. Right, so the energy liberated, so the delta E, the change in energy, is equal to mc squared, and that is going to be equal to 5, I'll chuck some brackets around this for your calculator, 0.229 times 10 to the negative 3 times 1.66, the conversion factor, times 10 to the negative 27 times c squared. So 3 times 10 to the 8 squared. Cool, and that all equals 7.81212 times 10 to 13 minus 13 joules. I'm just reading off what I've already done. Okay, so now we've got it in joules. We need to turn it into electron volts. So we know that the formula, well, voltage is equal to how many joules per coulomb, or they're the units for voltage. So voltage, another way to think about it is joules per coulomb, so how much energy per unit charge is being carried, I suppose, or the potential difference is. So that is equal to energy over charge, which is Q. And then all we need to do is just get the energy, 7.81, I'm not going to write the rest, but I would type it out in my calculator, times 10 to the negative 13. I'd write this whole number in the calculator when I do here, divided by charge on an electron is 1.6 times 10 to the negative 19. Minus as well, but it doesn't really matter because it's just energy, so you can just make it a plus. 4.88 times 10 to the 6 electron volts. Huzzah! We got 4.88 mega electron volts, which is what they're looking for. Right, next question. Using appropriate conservation laws, calculate the kinetic energy of an alpha particle and explain why most of the energy released in the decay goes to the lighter particle. Relativistic effects can be ignored. Right, let's just quickly check the masses. We have, so the initial momentum, radium initially at rest. So we have the initial momentum is 0, huzzah. Thus, we can say that the momentum of radium, so I'm going to have subscript R for radium, is equal to the momentum of the alpha particle. In other words, these two added together will sum to 0. So PR minus, or momentum of the radium minus the momentum of the alpha particle adds to 0, or they equal each other, just in opposite directions. So they equal each other in size. I mean, I could chuck a minus symbol in there, but it doesn't really matter. No, does it? That's a good point. No, they should sum to 0, so they should equal each other in size. I've never actually thought about that. Anyway, let's just forget about what I was just saying, because that might complicate things. Mass of radium times velocity of radium is equal to the mass of the alpha particle times the velocity of the alpha particle. In other words, we are going to get to this later, but I'll write it down because I'm going to have to read. So I'm going to have the velocity of the radium is equal to the mass of the alpha particle times the velocity of the alpha particle divided by the mass of radium. You wonder why I'm doing this. So my thought process when I'm doing these questions is I have to calculate the kinetic energy of the alpha particle. How I'm going to do that is I know the total energy of the system, and so I know the total energy of the system, and I want to write up an equation that has the total energy is equal to the kinetic energy of the radon particle plus the kinetic energy of the alpha particle. And I want to rearrange for the velocities. So I want to rearrange for the velocity because I know what the masses are, and if I can have an equation that only has one unknown, which is the velocity of either the radium or the alpha particle, I can find the velocity of the radium or the alpha particle. If you want to look into this question here is built upon in the 2020 question 3, the scholarship exam, question 20. I'm pretty sure it's question. I'm gonna pause it and find out. Yeah, it's definitely question 3 of the 2020 scholarship exam. Right. So I'm going to write an equation that explains the energy. So we're going to have the kinetic energy of the alpha particle plus the kinetic energy of the decay of the radium particle is equal to the total energy, which is 7.8 times 10 to the 13 joules. We already calculated that. It's energy that is liberated, which is just the deficit mass. Right, or I'll write this out, half mass of the alpha particle, velocity of the alpha particle squared, plus mass of, which should be a half in here, mass of the radon, velocity of the radon squared is equal to the total energy. Now you can see where I'm going. If I use this into here, I'll get an equation that only has knowns and one unknown, which is the velocity of the alpha particle. Then I can rearrange for the velocity of the alpha particle, find that number, and then I can put that back in to find the kinetic energy of the alpha particle, which is what it's asking for. And then we'll do our final little write-up at the end. So what we're going to have to do is we're going to have to substitute in this here into this equation, and then maybe cancel some stuff out. So I'll times everything by 2. So I'm going to have, I'll do it here, mass of the alpha particle, velocity of the alpha particle squared, plus mass of the radium, I want to say radium, times, and that is mass of the alpha, velocity of the alpha over mass of the radium squared is going to be equal to 2 times the total energy, because I just times both sides by 2 to get rid of the halves. Now I am going to expand this out. Am I going to expand that out? Yeah, I'll expand that out. That is going to be equal to mass of the alpha, velocity of alpha squared, plus, so we're going to have mass of the alpha squared, mass of the alpha squared over, and there's going to be velocity alpha squared over, and it would have been mass of the radium squared, but we've got the radium up here, so we can cancel out one of them. So this is going to be mass of the radium. This would have been squared, but we had mass of the radium on top. And that is going to be equal to, what's that equal to? 2 times the total energy. Cool. Now I am going to, how much room have I got? I'm going to pull v squared as the common factor for these two equations. I'm going to have v alpha squared, bracket, mass of the alpha plus, that should be alpha plus mass of the alpha squared over mass of radium, and that is equal to 2 times total energy. In other words, the the velocity of the alpha particle is equal to, I'm going to move this whole lot underneath the total energy, and then I'm going to square root because I need to undo that square root sign. So I have square root, they don't give you much room, do they? 2 times the total energy divided by bracket mass of the alpha plus mass of the alpha squared over mass of the radium, and that is equal to, let's check a wee tab down here. I'm going to run out of room for that. So that's going to be 2 times 7.81 blah 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 divided by mass of the alpha, which is the alpha particle, 4 times mass unit. Or you can do all this individually, so you can go 4 plus 4 squared, 4 all that plus that squared divided by the mass of what's R? Product Rn, that 222, 222 because it's the product. And then you times it by 1.66 at the end, and then you square it all out and you get a velocity of 1.53 times 10 to the 7 meters per second. I'm just running out of space, but I have done it on paper. This is a lot of these questions you have to do at the back of the book, so they give you bugger all space. So we have, and ask for the kinetic energy. So E K alpha is equal to half M alpha V alpha squared, which is equal to, if you just plug it in, I'm running out of room. It's going to be 7.77 times 10 to the negative 13 joules. And then if you divide this by the charge in electron, just like we did up here, to find it in electron in electron volts, that is equal to E K alpha is equal to 4.85 times 10 to the positive 6 electron volts. Right, so I'll quickly pause and just write the final little bit and then discuss it. Right, so I've said the alpha particle has a very high velocity. As v squared, or as velocity squared in the kinetic energy formula, it has 99.5% of the kinetic energy. If you get this number 4.85 and divide it by 4.88, you get 99.5. Going back to the 2020 scholarship question 3, this is essentially a mechanical impedance question, where you have 2 things undergoing some sort of collision. In this case, it's like an explosion, but conservation momentum all still apply. So the particle with the far smaller mass leaves with the same momentum as a larger particle, but because the ratio of masses is such that the smaller mass is like 200, it's 100 times smaller, it'll leave with 100 times the velocity. So it leaves with 100 squared of the energy. Right, that's enough about that. Next page, what do we got? The graph on the previous page shows a range of kinetic energies observed in electrons released in typical beta decay. There is we'll have a look at that graph. What do we got? Intensity, kinetic energy, mega electron volts, caps at 1.2, maybe about 1.15. And let's pretend it caps at 1.2. Intensity, I don't even know what that means, but I'll have a good look at it. There is a distribution that cuts off at some maximum kinetic energy, that was 1.2 mega electron volts. Initially, the researchers concluded that the products of beta decay were simply the daughter nucleus and a fast-moving electron, beta particle. Wolfgang Pauli used the above graph to conclude that there was some additional particle involved in the beta decay. Explain how this conclusion can be reached. Okay, so this is where history lessons come into play in knowing who Wolfgang Pauli was. If you're like a physics enthusiast, you'll know that Wolfgang Pauli is very famous for maybe like postulating the neutrino. It's neutrino is Italian for neutral, pretty sure. And if we look back at the graph, so I had to Google this because I knew roughly the history about how he discovered it, but I never knew about this graph and nor about the nuclear decay. So this is a plot of, I don't know, like maybe let's just say 100 different decays. So 100 different beta decays of the exact same particle. So you've got, I don't know, let's just pretend it's some, I don't actually know that many beta decays off by heart, but if you've got some particle decaying and you get a beta, like an electron released, they're looking at the exact same decay process every single time. And if you're looking at the exact same decay process every single time, you'd expect to have an electron which is way smaller than the mother nucleus, or the other nucleus. You'd expect the electron to come away with like 99% of the kinetic energy, which you can prove using mechanical impedance, because electrons are so much smaller than the other particles. However, if you look at this graph, I mean, a lot of the kinetic energy is just spread out over a large region, which means there must be some other particle lighter than the electron that's stealing the energy. Same way that the electron steals the energy, steals or takes away most of the energy in this collision, which is how they, I'm guessing, there would have been a lot of scientists who have been looking at this at the time and thinking there must be some other particle that's really light. In other words, it wouldn't be able to take off with a lot of kinetic energy of the electron. And for other reasons, that's not really talked about in this graph at all. If you looked at the actual decays, I'm pretty sure it's like if you looked at a neutron decay into a proton and a positron, the actual decay pattern, you'd expect if you had like a neutron just sitting stationary or just moving, trying to have it like stationary enough, you'd expect the proton to move off this way with some velocity and the electron to move off in the exact opposite direction with a far higher velocity. That wasn't observed a lot of the times. A lot of the times they'd move off, the proton would move off like this if a neutron was decaying, and the electron would just move off just a little bit to the side, which means there must have been some particle wiggling out that way, taking away a little bit of momentum. So that's how they suspected there must be some other particle at play. Right, I'll pause it, write up a semi-coherent answer, and then go through that. Right, so I've said when you observe a beta decay, you should expect to see the same beta kinetic energy for every decay, which is 1.2 mega electron volts. If nothing was getting stolen, or maybe like 1.15, because look at this one here. You'd expect to see him every single time, because it's the same decay, it should be the same, same energy. This is not the case, as there are a range of energies observed. This means there must be another very small particle relative to the electron moving away with some of the kinetic energy. Some is in meaning like a lot of the kinetic energy. Right, last question. What do we got? The rest mass of deuterium, 1 proton, 1 neutron. It's heavy water's constituent. It's there. If a proton and neutron are separated, the sum of the rest masses is slightly more, i.e. more than the original value. Yeah, sweet. You can compare those numbers because it'd be terrible. By contrast, if a rocket ship separates itself from a planet by burning fuel to escape the gravitational pull, then the total mass of the rocket on the launch pad is significantly more than the mass of the rocket after the escape. Compare and contrast these situations. So this is like the canonical, but it's the example that I give to my students when explaining binding energies. You've got to look at the whole picture. When you look at a proton and a neutron and you separate them, you have a proton, you have a neutron, and in order to separate them, like you draw a little box around them to make a system. In order to pull them apart, you need to put energy into that system. Cool. If you have a little planet, and then you have a little rocket ship. I don't know if I can draw a rocket ship. No, I can't even really draw a rocket ship. And you got the exhaust gases coming out the back. I'm terrible at drawing. You put a box around that. That's the system. There's no external energy coming in. Like none. None at all. So they're the same. Well, they're essentially the same thing. Here we have conservation of mass. Here we have conservation of energy, because you've got to put energy in to split them apart. So that's like the difference. So I'll pause it and try and write out a coherent-ish answer. Not that easy for this one, but yeah, and then I'll try and discuss. Right, so I've said in order to separate deuteron, you must overcome the binding energy, bracket nuclear strong force. This is external energy added to the system. I kind of missed the main point of the question, which is increasing its mass. If you add energy to the system, you increase its mass because mass is energy. It's equivalent to energy. With a rocket ship within the Earth rocket system, I got to the end and figured that out. With the rocket ship within the Earth rocket system, there is no external energy added. I mean, you could draw a picture around it. Exhaust gas is propelled from the rocket, sending it into space. However, the gas with its kinetic energy still remains inside the system, thus mass is conserved. So that's kind of the only difference. For atoms, you've got to put energy in. For rockets, I mean, it's contained within the system. For this question here, question C, I'm going to chuck a video in the description that goes over way more in detail the history of the discovery of neutrinos, which is, way better than I could ever do.